Not all storms are the same, and you've probably noticed that when looking at tornadoes and major severe weather outbreaks that have happened over the past years. You've probably heard terms like supercell, or the National Weather Service mention that a QLCS line is forming. But what does this mean, and why do storms take on such different structure? All of these questions come down to one thing: storm mode. In general, you could break down storms into three main types: supercells, QLCS systems, and single and multicell type thunderstorms. Out of these, supercells are the most well known. Supercells are long-lived, highly organized thunderstorms characterized by a deep, persistent, rotating updraft known as a mesocyclone. Out of all the storm modes, supercells are the most destructive, producing the biggest hail and the strongest tornadoes. When you think of supercell tornadoes, you probably think of EF5 level type of tornadoes. You might think of examples like the Joplin, Missouri tornado that happened in 2011, or even as recent as March 10th with the mega supercell that we had in northern Illinois. On radar, some key features of supercells include things like hook echoes and strong persistent rotation with intense velocity signatures. Supercells are also discrete in nature, meaning they remain separated from surrounding storms while having enough wind shear and instability to sustain themselves. Visually, when a supercell approaches, you can often see a defined structure, including a rain-free base where the updraft is located. This is also where features like wall clouds and sometimes tornadoes can develop. Supercells can have different structures like high precipitation supercells, and because of how complicated they are, I will be breaking down the anatomy of them in a separate video. But not all storms are isolated like supercells. In many cases, storms may organize into a line. This storm mode is known as a QLCS, also known as a quasi-linear convective system. Instead of one dominant storm, you have a line of storms all interacting with each other. These systems are usually long-lived, fast-moving, and often form along cold fronts and other boundaries. Within these lines, different structures can develop that change the impact of these storms. One of the most common is bow echoes. This is when a part of a line pushes outward, creating a bowed shape on radar, and it's typically associated with strong straight-line winds. Bow echoes are also a defining feature for systems like derechos. These are large, long-lived events capable of producing widespread wind damage, sometimes exceeding 100 miles per hour. Within these lines, small notches can develop, allowing air to rotate, which can lead to short-lived tornadoes. These are known as embedded rotation. QLCS systems can develop areas of rotation that last a lot longer than most brief spin-ups along the line, but still don't compare to the strength and longevity of a supercell's mesocyclone. No matter the structure, QLCS systems often produce insane visuals, including large shelf clouds and frequent lighting. Compared to supercells, these storms typically produce shorter-lived and less intense tornadoes. And that difference in structure is why storm mode plays such a major role in tornado risk and damage potential. There are also storms much less organized than this that you probably experience multiple times throughout the year. Single-cell storms are often short-lived and often called pulse storms because of their life cycle. They go through three steps: developing, maturing, and weakening. As the storm matures, precipitation begins to fall, and that rain-cooled air cuts off the updraft that's feeding the storm. So instead of sustaining itself like a supercell, a single-celled storm just collapses on itself. Multicell storms are a step up from this, with multiple cells forming and weakening within a close proximity. This allows the system to last longer and produces slightly stronger weather than single-celled storms. But still, nothing comes close to supercells and QLCS systems. So these are the storm modes, but why do storms organize like this in the first place? It all comes down to how the environment comes together to support organization of thunderstorms. In order for storms to initiate, we need lift, and often that comes from frontal zones and boundaries. These boundaries not only initiate storms, but can also influence what storm mode develops, depending on their speed, structure, and interaction with the environment. Boundaries themselves are complex and deserve their own full breakdown. Another key factor is instability. Instability is fuel for thunderstorms. When warm, moist air near the surface rises through cooler air above it, it creates buoyancy, which allows strong updrafts to develop. But even in environments with extreme instability, like in the summer, you could still end up with pulse-like storms, and that's where wind shear becomes critical. Wind shear is the change in wind speed and/or wind direction in height, and it plays a major role in how these storms organize and develop. All of these factors come together to shape storms, and that's how forecasters determine what storm mode is most likely on any given day. But more importantly, storm mode doesn't just tell you what the storm looks like, it tells you what the storm is capable of. Whether it's a short-lived pulse storm, a fast-moving QLCS line, or a long-lived supercell. The structure of that storm is ultimately what controls what severe weather is produced. And once you start to understand storm mode, you stop just watching storms. And this is exactly what I've been analyzing in my own data, looking at how storm mode, boundaries, and the environment all connect to tornado intensity. Because once you understand the environment, you understand the storm.